our second session. So the speaker is Dr. Yuki Orikasa from Ritsumeikan University. Orisaka sensei.
Thank you. I'm Yuki Orikasa from Ritsumeikan University. First of all, I would like to thank to the member of the Nora Japan for giving the opportunity to introduce my research topics. Especially Kato-san asked me to talk about battery, not including electrolysis. So today my talk is battery of future, insight of and challenge from advanced analysis. So in 1800, Alessandro Volta in Italy have invented first chemical battery. Japanese say Volta Denchi. So this is first battery and starting point for the later battery systems. And in 1991, Sony in Japan was the first to commercialize the rechargeable lithium-ion battery. Thanks to the innovation of lithium-ion battery, many small electronic devices such as cell phone, camera, laptop PC, power tool, and game are now used in all over the world. So at this moment, the demand of lithium-ion battery is increasing much more, as you can see here. So application of lithium-ion battery is expected to the electric vehicle and the smart grid and energy storage of renewable energy, and also drone. So this is a schematic image of the inside of lithium-ion battery. So lithium-ion battery is basically composed of three elements: cathode, anode, and electrolyte. So for the charge reaction, lithium-ion is extracted from the cathode material, and lithium-ion is inserted to the anode material, graphite layers. And then the electron is moved from the using the outer circuit. And also for the discharge reaction, the basic reaction is opposite direction. So lithium-ion is extracted from the anode and into the cathode. So for the charge discharge reaction, the structure of electrode material is basically unchanged. Only lithium-ion is moving during charge discharge reaction. So this types of reaction is called the topochemical reaction. So this topochemical reaction is one of advantage for the long cycle, because shape during charge discharge reaction, shape change is not occurred. So basically for lithium-ion battery, there is advantage for long cycle charge discharge reaction. So the Nobel Prize in Chemistry in 2019 was awarded to the development of lithium-ion battery. As you know, this week is Nobel week, so I also waiting. There is three breakthrough of development of lithium-ion battery. Here, Professor Whittingham developed the electrochemically lithium-ion insertion and extraction using electrochemical driving force. Professor Goodenough find the transition metal layer types oxide, which improves the operation voltage of lithium-ion battery. And also, Dr. Yoshino from Japan make a rechargeable battery system using non-aqueous electrolyte and carbon-based anode. So combined with the development, nowadays lithium-ion battery can be prepared. This is a word from the Nobel Committee. So of course, lithium-ion battery changed our lifestyle by emergence by the mobile phone and the laptop, but also it is important to it is very important for the lithium-ion battery possibly make an important role for fossil fuel-free society in the future. Unfortunately, at this moment, the production of lithium-ion battery make huge energy. Production of lithium-ion battery use huge energy. So at this moment, lithium-ion is not for the fuel-free society, but in the future, it is expected. So this is a development of electric vehicle after the 2000. So around 2000, Toyota lead making battery-based electric vehicle. In 2010, Mitsubishi and Nissan launched the pure electric vehicle, and also Tesla also launched the Model S. At this moment, 10 million electric vehicle is now used in all over the world. Also, Ferrari will launch the pure electric vehicle soon, I heard. Actually, I bought a new car this year, and I compare the pure electric vehicle and hybrid vehicle and fuel cell vehicle. And for fuel cell vehicle, my wife reject because not fuel cell, because space is very small. So my child may not accept. And also, I know that this advantage of pure electric vehicle because distance range is not comfortable for me. So at this moment, the driving distance is limited about 200 kilometer or 300 kilometer. Recently, the performance of lithium-ion battery is increasing. So new electric vehicle can move 300 kilometer, but for the gasoline vehicle, more than 500 kilometer can be moved per charge. So we need future battery system to overcome the conventional gasoline vehicle. At this moment, 90 million car is made in all over the world per year. So if we develop new battery system, we may have a big money. But development of new battery is not easy. So this figure shows weight energy density and volumetric energy density of battery system. So if the point on the right side, the battery is light, and on the top side, battery is compact. In the conventional lead acid rechargeable battery, as lead acid and sodium sulfur is located here. This is not for the portable devices, because these are smaller energy density compared with the lithium-ion battery. After the development of rechargeable nickel metal and lithium-ion battery, the energy density is significantly improved. So at this moment, this type of battery installed in the portable electronic devices. But this battery system is not suitable for the electric vehicle. So we now want to find new battery system like a fluoride ion, multivalent metal, lithium sulfur, or solid state battery, and also lithium-ion batteries. So researcher studied for many decades after the maybe 2000. We know there are still many disadvantages of using these types of battery. Even though the theoretical energy density of this type of future battery is very high, but stable operation cannot be achieved at this moment. So to improve the battery performance, we have to know the elemental reaction based on the electrochemistry. This shows the space and time scale of reaction of lithium-ion battery. So X scale shows the spatial scale, and Y axis shows the time scale. The starting point of the electrochemical reaction is the electrode-electrolyte interface, where the charge transfer reaction is occurred. And then, for the lithium-ion battery case, the lithium ion is stored to the active material, which is about 1 micrometer or 10 micrometer scale. But only 1 micrometer ion cannot be stored for the real battery operation. So we need to make a 3-dimensional structure using composite electrode, as shown here. The thickness of electrode is about 100 micrometer, and for the battery pack, the scale is about centimeter. And also reaction is also minutes or 1 hour scale. So to improve the battery reaction, so we need to every elemental reaction, because if some reaction stop, all reaction cannot be achieved. So also we need to analyze all elemental reaction based on the electrochemistry. Of course, we can perform the charge discharge, and we analyze the charge discharge profile and also impedance analysis. But actually, only impedance and charge discharge data cannot detect the inside specific behavior. So there are 2 types of reaction in homogeneity inside the lithium-ion battery. Let's show the reaction distribution of the cathode and anode active material of the composite electrode. So basically, for the reaction in composite electrode, electric conduction and ionic conduction both should be supplied. Of course, there is different reaction resistance for any part for the charge discharge in reaction distribution may occur. Right side is concentration distribution due to the mostly mass transfer behavior. So for the transport number of electrolyte using in lithium-ion battery is about 0.3. So for the initial state, the concentration is similar, but during charge discharge, the concentration of lithium-ion salt is not uniform. So we analyze the two types of inhomogeneous reaction of lithium-ion battery. So this is one of the results. So we use NCM cathode material, and by using confocal operand X-ray XRD analysis, we can detect the state of charge at across the electrode. So this color corresponds to the electrolyte side, and this color corresponds to the current collector side. And y-axis shows the state of charge, and x-axis corresponds to the discharge time here, and this is the rest time. So at this moment, there is no reaction distribution, but during discharge reaction, this part is reacted, but the inside part is not reacted also. But in 30 minutes after stopping discharge reaction, these types of distribution is disappeared. So in most cases, we disassemble the cell and check the state of charge. In some ways, we cannot detect the reaction distribution inside the electrode. So these types of temporal reaction distribution may affect the real charge-discharge behavior. So we need to optimize the composite electrode structure. So another distribution is electrolyte concentration distribution. So to analyze the electrolyte concentration distribution across the electrode and the electrolyte, we use a high-energy X-ray imaging technique. So high-energy X-ray can penetrate the lithium-ion battery cell, so we can directly detect the concentration distribution across the electrode and the electrolyte. So this is the result. So y-axis corresponds to the lithium-ion concentration, and this part is cathode and this part is anode, and the center is electrolyte part. So during charge reaction, the concentration of lithium is increasing on the anode composite electrode. So, and also cathode concentration is decreased. This phenomenon is maybe not detected in the water-based electrolyte, because basically the conductivity of water electrolyte is much higher than the organic electrolyte. For the lithium-ion battery case, the organic electrolyte is used, and maybe many phenomena is slow compared with the water-based electrolyte. So this, okay, so before that, so this phenomena affects the real battery performance, because the concentration of lithium ion of electrolyte change the real ionic conductivity. So in some parts, the ionic conductivity is much lower than the other part. So this decreases the charge-discharge capability. So this is a comparison of liquid types lithium-ion battery case and all solid electrolyte case. So left shows the liquid electrolyte, and y-axis corresponds to the concentration of the PF6 anion. So supposing charge neutrality, same concentration distribution is occurred inside the electrolyte. So during lithium-ion depositing on this side, concentration is also changing during changing. However, for the solid electrolyte, there is no concentration distribution here, only changing of the shape due to the silver deposition on this side. So when using the all solid state battery, the concentration of an ion is almost constant during charge discharge. This is very, very important for the application of all solid state battery because the concentration is one of disadvantage. Concentration distribution is one of advantage for the high rate charge discharge of lithium-ion battery. So after this finding, we know all solid state battery possibly improves, possibly exceeds the charge rate capability of lithium-ion battery. This difference is based on the transport number of ion of electrolyte. However, we have many disadvantages of all solid state battery. It is easy to image the contact between some material, like electrode active material and electrolyte. So to analyze the contact state of all solid state battery, we apply the X-ray CT. X-ray CT, maybe you know, is very powerful to detect the morphological change. And also, if we use the synchrotron X-ray, we detect directly morphological change during charge discharge. And this is silicon active material here. So we study the contacted state between the silicon active material and the electrolyte during charge discharge. So this figure shows the charge discharge profile. And also, we measure the X-ray CT by using same cell. And this is a silicon active material. During charge, silicon is expanded due to the lithiation of silicon active material here. And then for the discharge reaction, silicon is shrinked due to the extraction of lithium ion. And also, for the subsequent charge discharge, silicon is expanding and shrinking. When I look at this figure, actually I disappointed because this case, lithium ion cannot be supplied to the active material, so many of the reaction may be stopped. However, after the first charge discharge, the reaction can be proceeded. So, what is the reason of this? When we look closely between the silicon active material and electrolyte, we know the reason why the cycling of all solid state battery can be achieved. So this is the silicon active material, and for the discharge reaction, silicon is shrinked here, here, and here. So the contacted state between silicon and electrolyte is lost. However, when looking here, partial contact using the bridging between the silicon active material and electrolyte is maintained, even though most of the contact is lost. So this is a discharge state, but using this small contacted bridging state, lithium ion can be supplied. So for the discharging reaction, lithium ion can be supplied and silicon is expanded, the reaction can be proceeded. And also, when looking the charge-discharge cycling, compared with the lithium-ion battery using silicon anode, all solid-state battery shows a good cyclability here. Only irreversible capacities of the first cycle and subsequent cycle can be achieved without capacity loss. So based on the analysis of the contacted state, we know the reason. So this is a CT image after the 6th cycle and the 9th cycle. Of course, the contacted state is very smaller than the conventional, than the usual state, but the shape change is reversible. So for the discharge state, only this point can have a role to supply the lithium ion, but the shape change is reversible. So this is one of key point for the charge discharge property, charge discharge cyclability of all solid state battery. Okay, so now let me summarize my talk. Conventionally, lithium ion is developed for the mostly convenience and economy for human life. So, and this nowadays we know that this advantage of lithium ion battery, like fire problem and cost and environment. So in the future, we have to consider these types of issue, and also including the electrochemical reaction inside the lithium ion battery. And also, future battery case, we need to consider these types of topics, and of course, the chemical and electrochemical reaction should be stable and safety. So maybe electrochemistry have a crucial role for the development in the future. So I would like to thank to the Professor Yoshimoto, maybe he's not here, and for the CT measurement support from the Japan Synchrotron Radiation Institute. And also we discussed the company member and my group. Okay, thank you for your kind attention.
So I believe Orikata-sensei is happy for receiving questions or comments.
I think you mentioned for the liquid electrolyte lithium battery that there is distribution of the lithium ion during the charge discharge, and for the solid state there's no that kind of phenomenon. Do you know why this difference between these two electrolyte and from the analyzed technology?
Okay, for the electrolyte, right?
Yes.
Okay, so for the solid state case, the transport number of carrier ion is about 1. So only carrier ion is moved during charge discharge. So Japanese say tokoroten, hopping. So for example, anode release the lithium ion. This lithium ion push the lithium ion around the cathode, and this cathode, for this cathode, lithium ion accept around the cathode material, electrolyte around the cathode material. So this is a type of hopping reaction. But for the lithium ion battery case, the moving of the carrier ion also an ion, like PF6. So in this case, both both carrier is moved, and during charge discharge, the diffusion should be occurred. So this is the reason for the concentration distribution for the lithium-ion battery.
Any other questions, comment? Nora, please.
Yeah, thank you for the very nice talk. So I was wondering, when you have liquid electrolyte, you make solid electrolyte interface. So do you see similar interface in the solid electrolyte as well?
So interface between electrode and electrolyte for liquid case is totally different from the solid case. So typically, the contact state of this liquid case is 100%. So in this case, only decomposition product disturbs the reaction. So from this, the basic concept is totally different between solid and liquid.
Okay. Thank you.
Thank you.
Okay, then let's thank again to Dr. Orisaka for his nice presentation. Thank you.
Thank you very much.
Okay, so the next presentation is from Dr. Alessandro Fiorucci. Okay.
Thank you, Yasui-san. Thank you all for attending in this beautiful venue of this international exposition. Let me start from one point. We have seen throughout Yoshida-san's presentation what the Nora does. All the business that we work on. Here, the presentation will be very linked to one specific business and actually one specific technology within that business, that is alkaline water electrolysis. A brief summary of what we will be discussing. A general introduction regarding what is alkaline water electrolysis, may be trivial for many of the attendees, but worth going through that. A clarification that is always important for us. Why is hydrogen important as a general media and how to obtain that? An overview on the timeline. We would like to use the Nora experience over 100 years as a reference, as an example to what can be done in the solution. Go through with an example of the early industrial solution that the Nora has presented in the past. What is the present configuration with the Dragonfly system, for whom you see an example on there. And then the most difficult portion that is always discussing about the future of the hydrogen scenario. What is alkaline water electrolysis? So basically is electrolyzing water to obtain oxygen and hydrogen especially. The media and the reaction is done in an alkaline media, in a liquid alkaline media, in order to achieve, to reduce as much as possible the power consumption of the system. Typical configuration nowadays in the range of 30%, plus or minus 3%, in order to exploit the best conductivity, basically window for KOH in aqueous solution. Temperature-wise, 80, 90 degrees. Actually, I would say 70 to 90 degrees. Also in this case, the higher the temperature, the better the power consumption. The lower temperature is a safe harbor in order to ensure resistance of the components applied. So also in this case, can be considered as a trade-off. Pressure. We know very well that there are, especially on the larger installation, atmospheric configurations are the most common and I would say are the most applied, while on the smaller installation, I would say in the range of 1 to 10 equivalent megawatt kind of configuration, pressurized. And when we say pressurized, especially in the European business, means usually 30 bars as a configuration is the most applied. Pertaining to current density, we see also here a very large range. You know the Nora's role as a supplier of electrodes, high-performance electrodes. So, of course, we are keen to exploit high current densities for the application. We know that in some other cases, a lower one is applied. Also, in this case, it's a trade-off in terms of specific power consumption between one and the other. So it's really linked to the performance. Eventually, compared to other traditional technologies, the separator is not really a membrane, but is typically a porous diaphragm. Usually, so we don't have ion exchange properties as we have seen in some of the application we have seen before. What is the general configuration of a plant? Of course, everybody looks at the stack, that is the core. The reactant is basically water coming from a circulation. Depending on the technology supplier, each and every one is really changing this in order to ensure how to keep the concentration stable and in order to exploit the best operating window in terms of KOH concentration. And the other reactant, as correctly stated before, that is basically current fed to the stack itself. Water in order to rebalance the generation. This is basically, apart from water feed, a closed system in terms of KOH supply. Oxygen is usually cooled in order to avoid loss of humidity, a large loss of humidity in this part, and is usually vented. Hydrogen is then treated, and after separation can be applied at the oxygenation unit. This is really linked to the request from the final customer. Then a dryer, again, to be sure to have an hydrogen that is both suitable for the application and to be sure that we collect all the humidity in the closed loop. And then typical configuration sees a low pressure buffer tank. And depending on the application, this is really customer driven also, a compression set, a compression unit, and a high pressure storage. So for the most, the concept is general, but I would say each and every bit has something that depends either on the customer or on the technology provider itself. One general note before going on, otherwise there may be some misunderstanding. I think you are most likely all familiar anyway with the so-called levelized cost of hydrogen. For those of you who are not, the concept is very similar to the so-called TCO, so total cost of ownership. It's not just taking a look at a technology based on the investment, initial investment, but it's taking a look at the overall value brought by the same technology there, right? So what we see, okay, are some general indicators of the installation that we can be interested in. The most interesting, in my opinion, is the specific energy consumption. So what is the actual, we have seen it also in previous presentation, but is what is basically the energy cost, somehow, the energy amount that we need to pay in order to achieve a certain production, and what are the actual expectation in terms of lifetime of the installation and operating hours. On the other end, apart from the same KPI, the specific energy consumption, the big question mark is pertaining what is the cost of energy. There are then other basically operating costs or the other voices or other items that can be seen as operating costs, such as the maintenance, basically, that can be considered as an OPEX. All of this concurs to generate the so-called LCOH. Pretty straightforward. We said hydrogen. I never speak explicitly, or I try to step out of speaking only of green hydrogen. There are many reasons, anyway, to justify what is the reason why we need hydrogen. Hydrogen can be foreseen either directly or indirectly through other chemical species generated through hydrogen as a possible energy carrier to support the energy transition without requesting a reduction in terms of industrial application, of course. The reason for it, this is just one of the many that we can provide, is the global warming, basically, and the driver for it, right? So it is definitely an interesting energy carrier, also because it has several alternative applications or several alternative routes where it can be applied. We discuss about green hydrogen, whether we have a source of energy that is renewable. There are definitely some usage for it that are direct, basically as a potential fuel, as applying it directly, or also, very interestingly, by transforming it either through, most typical can be considered ammonia, but also in other e-fuels, as a possible basically other type of carriers. This is specifically very interesting when we come to the so-called hard-to-abate industries, where the impact in terms of pollution and basically the impact can be very, very, very significant. There are also other applications where hydrogen can be seen as a direct fuel. They can be exploited. Of course, hydrogen is not, we all know, is not the best fuel in terms of basically specific heat capacity. We discuss why hydrogen is necessary or why hydrogen is interesting. On the other hand, the question is how to obtain that. We know that there are basically 4 families in terms of technologies to produce. Out of this technology, definitely alkaline water electrolysis is the most established, especially in terms of large plants, large installations. There are several advantages in this case for alkaline water electrolysis compared to the other ones. I am sorry that I depict basically a scenario from 2020 to 2050. This is an old picture from IRENA, but I have to say, depending on the report, the number can vary, but the scenario, I would say, is still the same, right? So the most interesting point, let's say, in the current, more or less, scenario is the energy efficiency of a system that can be still considered in line with PEM electrolysis, probably on the high end even a little bit better. And of course, there is a big advantage in terms of investment of the technology itself. As mentioned, we would like to use some example out of the Nora experience as an example of the technology itself and its application. More interesting to me than the previous table is this graph, because it seems very straightforward, very easy to understand in terms of impact of the technology and what are the different and how basically the different variables are playing a role in the introduction of the technology itself. What you see are basically 2 curves. The difference between these two and these two is only pertaining to the electrolyzer costs, so to the initial capex. That has, of course, a value. This is the foreseen reduction that we expect in time. We know that basically going from more costly to a cheaper electrolyzer would play an impact. As we can see from the top curve, not necessarily is enough to achieve what is the current basically cost for, or levelized cost of hydrogen for a gray hydrogen, for an hydrogen obtained from, let's say, carbon sources. What is playing the most or the highest jump, going from the red to the dark green and going from the, let's say, orange to the light green, is the energy cost. This is a little bit misleading. So it's not only energy cost, but it's also specific power consumption. So what it means is, at the end, how is that portion entering in my levelized cost of hydrogen, and how is it affecting the cost of the hydrogen I generate? So out of the two, the investment that I need to pay upfront for my plant and the energy that I consume and, of course, that I pay for, definitely the latter is the heavier. This is pretty evident, basically, from this jump, and is basically necessary in order to step in the gray zone. That is when the technology can be interesting and competitive against gray hydrogen. Just an example to confirm what we are saying. This is a graph out of literature. Same technology, same capex, same cost, same everything. The only difference being the energy cost at the end and the way it's supplied. So we have a case from Germany, just as an example, with 4,000 hours per year, basically with a typical cost of energy, let me say not even on the high range of what you can pay in Europe, so 120 euro per megawatt hour. And we have, it's very hard to read, but basically what we have in terms of levelized cost of hydrogen is a number that is in the range of 11 euro per kilo. And on the other end, what we have with the same kind of technology, but with a PV case, with a much lower availability, because we know that in this case it's a PV, so the solar energy doesn't have the same availability. We have a cost of hydrogen that is basically less than half of the previous scenario. So we know that the impact of performance and of cost of energy has a huge impact on the scenario itself. I mentioned that I would have used the Nora experience in the business to go through what was the technology, what is the technology today, and a big question mark, what will be the technology tomorrow, what will be the scenario for hydrogen tomorrow. We understood that the company was founded in 1923. We depicted a scenario for early industrial solution. We could see and we could trace first our electrolyzer from the Nora already right after its founding, with application ranging, for example, also considering the use of oxygen as a welding gas. The larger, anyway, installation were, let's say, in the 50s, end of the 50s and the 60s, with a reduction due, we will see why, but let's say mainly to the competition by gray hydrogen. Then we will go through what is the current solution that the Nora is in the pipeline for hydrogen generation. And we will go at the end, at what is going to be the scenario for the future. Let's take a look at the past of hydrogen evolution. The first large application we could trace back from the late 50s, I would say, would exploit hydropower and an excess of hydropower in order to generate, let's say, green ammonia back then, or anyway, nitrogen basically based fertilizer. Being an excess of power or driven by excess of power, there were not so much focus on the specific power consumption. Although I have to say, and we will see on the next slide, the values were not so horrible compared to other technology. As mentioned, basically the energy price, the hydrogen price from gray sources would, at the end, let's say around the 70s, shift out these kind of applications as installed. Here I speak about low productivity, so low current density. What do we mean as low current density? Would mean basically a scenario as the one we see here. We use the first large installation, so this Nangal plant, roughly 150 megawatt equivalent production as reference. What we would have is at the beginning, so in 1959, a current density of about 1.2, 1.5 Ka meter square. The power consumption at those values would be in the range of 52 to 55, let's say, kilowatt hour per kilogram at stack level. So higher than what we have seen as a scenario for 2020, but let's say not so higher. Interestingly, there were some limitations pertaining to KOH concentration and temperature. This was mainly driven by material availability and resistance. So low concentration, lower temperature would allow a longer life of the equipment. The installation was an atmospheric installation by itself and was exploiting natural circulation. A couple of special features, because for me it was interesting. rediscovering these and taking a look at that. One is a dedicated cooling circuit within the electrolyzer that is not standard, but we can detail a little bit better in the next slide. The other is how to maintain a safe condition for operation with a limitation on the available materials. What they would exploit is a zero gap up to the separators, but they would use basically two separators with a mixed chamber that would collect the so-called mixed gas. So in order to avoid cross-contamination from anodic chamber to cathodic chamber and vice versa, it would basically have an intermediate chamber to collect these liquids. Is unfortunately not so easy to see, but the document is pretty old. We have seen the past. Let's take a look at the present of what the Nora is pursuing and how to link these two steps. In the last 5 years, more or less, the Nora has been working on a project for a so-called Dragonfly system. It's basically the evolution of a classical water electrolysis technology. The goal was originally to pursue minimization of the footprint. We know that PEM electrolyzers are very compact due to the high current density and to the no need or less need of treatment of gases after production. And on the other end, the other request was, of course, an optimization on power consumption. So increasing the current efficiency, as also in this case for Ayoshida's presentation on what is the impact on the basically Faradic efficiency and on operating pressure. The solution itself is this is an example of a megawatt installation, so roughly 200 normal cubic meter per hour kind of installation can be seen basically here. The concept is to have a system that is hopefully a turnkey kind of condition with a process portion of it installed within all the utilities needed. An air package for supplying, of course, all the valves and all the instruments, a nitrogen package in order to ensure a safe operation, demineralized water generation. On the other end, there is the core of the plant that is basically a stack with pertaining the gases that we have seen in the PFD before and the post-treatment basically package itself. The system is also equipped with let's say, the main power and all the utilities necessary to generate hydrogen and to sustain operation. So at the end, this should be seen as a sort of a black box where water enters, power enters, in this case, not current, and basically hydrogen and oxygen is discharged at the battery limit. More in terms of comparison to what we have seen from the past, the condition is very different from many standpoints, but there are some points of continuity. Of course, we were on the 23%. Here we can exploit what is the current status, so we can go at much higher concentration, exploiting a better power consumption and much higher temperature. So over 80 at the moment, we are targeting a rough 85 degrees in terms of operation. It's a pressurized condition. This is very much linked to the levelized cost of hydrogen that we have seen, especially on smaller installation like this one, that is a 1 megawatt. The impact on the LCOH of the compression unit would be extremely heavy. So in order to avoid that, it makes more sense to go for a 30 bars. And a current density that can range up to the maximum, basically, that can be achieved in the market at the moment, that is 12 km meter square. Of course, what we can do is play with the request in terms of power consumption in order to adjust that. Of course, with this kind of current densities, it goes without saying, forced circulation is necessary. One interesting thing is that what we exploited was also in that case a dedicated cooling circuit. So this is in continuity with what was done roughly 70 years ago. This was done in order to reduce the amount of KOH circulating. We know that in the case of alkaline water electrolysis, differently, for example, from chloralkali business, we have a closed loop So with basically a fixed amount of KOH that it is circulating, and this allows to reduce that and to reduce the impact in terms of capex on these items themselves. And on the other case, this is a turnkey configuration, so to minimize basically the activities at site. This is not just a render, but as we could see from the picture before, is also a part of a funded project by the European Union. This is installed in northern Italy within this Tenova site. In this case, hydrogen is used as a fuel for a mixed stream burner. So it's a burner that can either work on methane, hydrogen, or mixed stream, basically. And basically, the concept is to prove that it can be fully integrated, going from a PV that is installed on the roof, so a green power available, up to the hydrogen generation from the Nora electrolyzer and up to storage and use within this system itself. The final goal of the project itself is to achieve production of green steel, so in order to ensure a better, a lower, basically, CO2 impact on this technology itself. Some more picture regarding the installation itself. What is interesting is the fact that basically the unit is fully automated. Of course, we need to operate at the moment, but the operating states of the machine itself are automated as much as possible. This is also to avoid having an intervention of operators within the unit itself. We discussed the past. We took a look at the present. I am in the difficult condition to try to predict something regarding the future and regarding the trends. We have seen this graph previously. The thought I had was how to prioritize what we have seen here in terms of goals and what is really important. I tried to provide 3 levels and a 4th one that I didn't write down, but I think is worth undergoing. The main one, I think, is pretty straightforward, is the request in terms of power consumption, specific power consumption reduction. We cannot control, of course, the cost of power. It depends on the request from the final customer and what is the installation like. But the most important point where we need to work on is the specific power consumption of the overall system. In this case, we don't provide just a stack, but we provide everything. So at the end, the kilowatt the customer will pay, he doesn't care whether it goes in a stack or in a system to purify water. He's blind from this standpoint. The second one we mentioned is basically capital cost range. So what is going to be the cost? This is even a more extreme jump. So the request is to go at least with a factor 2 or higher in order to reduce the capex. It's going to be extremely difficult. Also, out of the 2, of course, we have seen that the OPEX portion is the more heavy. So my personal opinion is that we should work more on the last one. The third topic is pressure. We have seen that the standard, especially for small installation, is to go to 30 bars G. Here the request was to go even higher than that. This report is specifically pertaining to large installation, 100 megawatt. So what I would encourage is really taking a look at what is the usage of hydrogen and what is the unit going to be installed in. And I go to my fourth point, that is, here we see basically an electrolyzer or a system as a standalone kind of equipment. Of course, to improve the pressure can be an interesting topic, but it's really depending on what is the hydrogen usage going to be. Because to increase this as an impact and can have a much higher impact in terms of levelized cost of hydrogen on the electrolyzer than what could be the impact on storage and compression. Also, the other topic I would like to stress is, and that has never been stressed before, is to consider these systems as a standalone kind of condition is wrong, in my opinion, for another reason. Out of the energy that we use on the stack, two-thirds are thermodynamical, basically, but the rest is going to come out as ohmic power, and so is going to be put out as heat and is usually sent to the environment. Same as the oxygen, as you were mentioning before, Shida-san, that is sent to the environment. So we have a chemical, maybe not pure, that we are throwing away, and we have power, low value power, I agree, but some power that we are throwing away. So my opinion is that rather than setting extremely difficult goals, I would really be keen to take a look at alternatives to these two streams that are basically not exploited. We come from chloralkali business where we know very well that every chemical that is generated is valued at the very end. That's it. Thank you very much.
Okay, so Alessandro, thank you very much. Any comment, question from the audience?
Thank you. Thank you. Really interesting presentation. Well, I would like to ask something that is regarding to the power balance or the grid integration. Well, in our new design or in our system, is there any detailed discussion on, for example, how we can connect our device into a smart grid and to make it live longer and perform better? Thank you.
You're welcome. Thank you for the question. We had plenty of discussion, yes, pertaining to the so-called island kind of power connection. At the very end, at least in Europe, was never a solution that we've seen applied so much. The reply in terms of especially PV generation can be rather fast. In terms of smart grid, there are some, so not an island itself, but let's say an integrated portion of a larger scope. We also enter on a different project where basically we would be partially balanced by a battery system in order to ensure fully exploit, to be able to fully exploit the power generated by PV itself. The project is still ongoing, so I cannot reply at the moment, but is a part of the study. In my opinion, the concept from the power standpoint is still to consider the electrolyzer as a black box. So there is not. There are some literature studies for sure, but there is no complete knowledge because either one is a supplier of one technology or the other. So it is something that is still being studied. So.
Thank you very much. Thank you.
Maybe one more comment questions?
Yeah, thank you for nice presentation. I'm Shigenori Mishima from Yokohama National University, and the Dragonfly system have the 30 bar. Yeah, and when the system operate by the renewable energy, it must be fluctuate, and sometimes the power shut down. At that time, how you maintain pressure or decrease pressure? How do you operate it?
It depends, of course, on the case of the shutdown. Let's say that we are linked to a major shutdown, so a sudden lack of power. We do have installed a system in order to ensure safe, basically, the system to be put in safe mode. So if there is a lack of power for a continued period, the system can go in a safe condition. It's very different when it comes to rough, let's say, quick fluctuation, like when it happens to the PV. We know that we have seen from the Spain case, maybe 1,800 hours in a year, with a sort of Gaussian kind of profile, but that is a fake profile because we know that if we take a look at a short frequency, the power is going to offset like that. It really depends on the configuration of the power feed, in my opinion, because if the power is fed to the grid and then fed to the electrolyzer, in one case. The island case is very much different. So the system, and especially the alkaline water electrolysis systems we develop, have some transients. So I would consider, depending on the type of configuration, to have even a battery system to exploit that. We could see from literature cases of other suppliers, but I mean, is independently from the technology supplier, where the difficulty is really not to track the large Gaussian, but the small frequency variation, like a cloud basically passing through. So in that case, even a small BESS system or other kind of accumulation can be helpful. Of course, it has to be as much limited as possible, because otherwise the economics and the levelized cost of hydrogen will boost out of the roof. So for what we have seen so far in Europe, for the most, even when there is PV, there is not a real island for the most kind of configuration, but there is still a PV. Given the power generated is given to the grid, and you are compensated with the same amount of power at the same time, basically. Thank you.
Okay, so then please join to thank you, Alessandro, once again. Okay, so we coming to the final presentation. Mr. Naoya Matsuda from JX Advanced Material Research and Institute going to give us a talk.
Good day. Thank you very much for today's opportunity. I am Naoya Matsuda, in charge of copper and rare metal market research at JX Advanced Metal Research Institute for Technology and Strategy. Today, I would like to introduce you about copper and copper supply chain of mine and recycled materials. Yes. So, first, I would briefly introduce you about our company, and then talk about the copper, how much minerals are there in the world, and how the supply chain is today. And we'd like to introduce you to our hybrid smelting and sustainable copper. JX Advanced Metals is one of the 8 non-ferrous companies in Japan, and top copper producer in Japan. Also, as of 2024, we are one of the top 10 copper producing companies in the world. We are a global player in non-ferrous metal market, providing value to society and technology-based firm and global supply chain to support this goal. So we have two business of base business and also focus business. Base business consists of mineral resource and smelting and recycling. And focus business consists of ICT materials and semiconductor materials. So, talking about copper. What do we know about copper? It says that the first metal used by human being is copper around BC 7000 to 8000. And around BC 3500, Bronze Age started in Mesopotamia, Egypt. Bronze is an alloy of copper and tin, and used for weapons, tools, and accessories. Today, copper is used in various applications, such as smartphones, data centers, and EV, due to electrical and thermal conductivity. So, copper as a mineral. Now, how much could you mine? This is a graph of the copper minerals, and today, world copper mine production is 22.4 million tons of copper, annual base. And within the resource, amounts that we could economically extract is called reserves, which is, and copper reserves are estimated to be 1,000 million tons, which is equal to approximately 40 years of mining. And undefined resource is estimated to be 2,100 million tons. And total resource, which is identified and also undiscovered is 5,600 million tons. Please note that reserves is based on economical standpoint, which is, in the past, there was a big increase of 600 million tons here in year 2000 to 2023. Research based on technology updates and also copper prices. So now we know how much copper are there as a mineral. I would like to talk about how we make the copper mineral to copper ingot, which is called copper cathode. Copper cathodes are made by smelters, pyrometallurgy, and also SXEW mine by hydrometallurgy. By pyrometallurgy, mine makes a copper concentrate from the ore, which is copper content 0.2 from 1% to 30%. And smelter makes copper cathode from copper content, which is by copper content is 99.99%, which is 49. And the by hydrometallurgy process, copper ingots called SXEW copper is made at mine site, which is also the same content. The process depends on what minerals you have. For example, primary sulfate ore and secondary sulfate ore are processed by pyrometallurgy, and for oxide and secondary sulfide ore, these two are processed by hydrometallurgy. So, at the mine site, both open pit and underground ore is extracted and crushed and ground to several tens of microns. Using the hydrophobicity of mineral, the ore is separated into copper-rich portion and another portion. Adding water, reagent, and bubbles to the ore, sulfide ore is attracted to the bubbles, and copper is concentrated to 20 to 40% of copper. And after drying the concentrate, process is finished at the mine. So these are the world top copper mines. As you can see, many major mines is located in South America, such as Chile and Peru. Also, these are the operators of the big world top mines, and as a major mine operators tend to be the mining major companies such as BHP, Freeport, Rio Tinto, and Anglo American. So, by looking at the copper mine production, copper concentrate production is increasing mainly by Chile and Peru. Although SXEW production, which is the green one, the growth is limited due to availability of the oxide deposits. So, by looking at the copper mine production by countries, world top producer is Chile, which accounts for 24% of world production. Other leading producers are DRC, Peru, China, and USA. Recently, DRC is rapidly increasing its production. So, now I would like to talk about production flow of copper cathode at smelter using the blast furnaces. Blast furnace is a major copper smelting process around the world. The copper concentrates are fed to the blast furnace with oxide-enriched air. And in the surface, the concentrates, which consist of copper 30%, iron, and sulfur, are instantly oxidized. Copper concentrates are melt and separated by their own reaction heat into copper matte with a grade of 65% and slag. The copper matte is transferred to the converter furnace and anode furnace and refined to purity of approximately 99.5%. And anode plates are refined in the refineries, which is tank house, for electro-refining and copper cathode with grade of 99.99%. 49 are produced as a final product. When copper concentrates are fed into the blast furnace with oxygen, oxide sulfur will give excess reaction heat. And with this reaction heat, recycled materials such as scraps could be treated efficiently and also economically. So, this is a list of the world top copper smelters. As you can see, many major smelters are located in copper consuming countries such as China and Japan. Also, these are the world top copper refineries, which is also a tank house. As same as copper, major refineries are also located in copper-consuming countries. In other words, same location as smelters. So, world copper cathode production and consumption has both grown by CAGR 2.1% and 2.2% respectively by 5 million tons from 2014 to 2024. So, by country basis, copper cathode production is mainly produced in China, DRC, Chile, and Japan. China's copper cathode production has seen a rapid growth from 6.9 million tons in 2014 to 11.8 million tons in 2024, which is 1.8 times. And similarly, DRC has also seen a rapid growth of 10 times from 2014 to 2024. So, by country basis, copper cathode is mainly consumed in China and USA, Germany, India, Japan. China's consumption also increased very rapidly from 10 million tons in 2014 to 15 million tons in 2024, which is almost 60% of the world consumption. Looking at China, a share in the copper industry, as we have seen, China's copper cathode production and also consumption share is 44% and 57%. With not only production and consumption, China's import of copper concentrate and blister anode and also copper cathode are world #1. So now let's see how the copper is used. By first use, 74% of copper is consumed to make wire rods, and the wire rod is used to make a cable. The remainder is used for billets and cake and slab, which is used to make copper semi-products. By final use, it is relatively balanced by construction, electron networks, and industrial machinery, transport, and consumer generals. So, looking at industry global flow of copper, it goes from copper mine production, to copper cathode production, and copper semis production, and final products. It is estimated that it is 470 million tons of copper is used in the market. Within the industry global flow, 15% of copper. This is recycled materials, which is copper scraps, and used when producing the copper cathodes. And 15% here is also used for 15% of recycled materials used when producing the copper semis, finished goods. These recycled materials are mainly high-grade copper scraps here. And so, considering the ratio of copper scraps used in the flow, it would make up approximately 28%, which is 8.1 million tons. But unfortunately, 9.5 million tons of copper is lost in the global flow during disposed, collected, and separated. This lost amount, 9.5 million tons, is bigger than the 8.1 million tons recycled material used in the industry global flow. So, potential availability of copper scrap is huge. But challenges such as systematic collecting, separating technology, and cost tend to be restricting the increasing of the supply. In the last, I would like to introduce JEC's advanced method activity of green hybrid smelting. In August 2022, JEC's advanced metal groups formulated our sustainable copper vision. This vision reflects our recognition that copper is an essential material for achieving carbon neutrality and describes our policy for the supply and ongoing evolution of sustainable copper. Meeting the increasing demand of copper requires a stable supply of copper ore and recycled materials. While demand of copper will continue to grow over the long term, the supply of copper concentrate from existing mines is limited depending on the availability of deposits, investment, and permits from authorities. The supply-demand balance for copper is likely to be very unstable in the future. This describes balance and why copper ore and recycled materials will be essential in meeting the demand for copper, without which the world cannot achieve decarbonization. So, we offer copper products using the green hybrid smelting. As we've seen, both copper concentrate and scrap can be used as a raw materials. As of fiscal year 2024, JEC's advanced metals recycling ratio for copper cathode was 24.6%, approximately 10,000 tons. And we target to increase our recycling ratio to 50% by 2040. In order to develop and popularize sustainable copper, we have key 4 initiatives: reducing carbon footprints, increasing recycling ratio, promote responsible procurement and other measures, and form green enabling partnerships. So, in related to this sustainable copper vision, I would like to introduce JX Advanced Metals' two types of 100% recycled electric copper products and logo as an example. Both 100% recycled electric copper are applying mass balance method, which has already been applied for 100% biofuels, 100% recycled plastic, and aluminum. The first one is a patterned closed-loop 100% mass balance method. This product enables the copper incorporated in the customer products to be reintegrated back into customer's own products. The second one is mixed recycled 100% mass balance method. This product supplies 100% recycled electronic copper using mass balance method based on recycled materials collected from the market through the JX Advanced Metals Recycled Material Collection Networks. The company has also launched CU Again project, which aims to promote the social implementation of this product. CU Again expressed the wishes that electronic copper, CU, after completing its role in society, will be returned as a scrap and recycled repeatedly to support the future society. So, conclusion. Well, today, we know that copper reserves could be extracted approximately 40 years from today as a mineral. And also, world copper mine production are led by Chile, DRC, and Peru. China is a major player in the world copper cathode production and also consumption. In the world copper supply chain, 28% is already recycled material, although within the supply chain, 33% of copper is lost. By using copper smelting technology, a flash furnace, copper scrap could be treated efficiently and also environmentally friendly process. Thank you very much for your attention.
Thank you very much, Mr. Matsuda. So, any questions, comment from the audience? Please wait for the mic.
Thank you for your presentation. It's very interesting, and I want to ask about the treatment for to use the scrap copper to be used again to be recycled. What kind of treatment do you use? What kind of treatment?
Sorry, can I go back to my slide?
あ、
ごめんなさい、ちょっとスライドが出なくなっちゃった。
Can we operate the slide? Can you project the slide once again?
Thank you very much. So maybe I think this slide is good, the global flow. So in the industry, we are already using two types of scraps, which is for producing the semi-finished products. They can only use the high-grade copper scrap, which is around above 90% of copper content. Although, as a smelter, we can use both low-grade scrap and also the high-grade scrap. So the only problem for us is that it's a big problem for all of us, is systematic collecting. So it's everywhere in the society and the market. So we have to collect it efficiently and also by low cost. So it means that we need a system for collecting those things. So if we can collect it, it's very easily treated again to the copper cathode. But also there is but if we have other thing, for example, if we get from the PCs, there's other issues. So we need a pre-treatment, but also as a JX advanced metal, we also have a pre-treatment system, so it could be treated appropriately. But other issues, there are also precious metals included in those scraps. So there is some going to somewhere else which we could not know. So it's sometimes there's a gray market. So those are the issues that is avoiding us to make this little bit smaller. That is the situation. So as far as we can collect, or other people can collect, as a medium-sized or big-sized smelters, it could be treated properly.
Thank you so much. And I was thinking, like, I think mining from the ore is more cheaper compared to recycling, right?
Yes, but I think it's done by a completely different scale. So mine is providing much more bigger production, which is the remainder of the 72%. So it's much bigger, and we need also the mine also. But so copper recycling scrap materials is doing their role as a feeding the balance of the supply and demand, and also we need a copper mine to have the base amount of that demand coming through.
Okay, thank you.
Any other question, comment? So then, please join again to thank you. Okay, so we finished all the presentations for this symposium. So we're going to move to the closing session. So first, we have a video letter from Italian embassy. So please have a look of that.
Dear Ambassador Battani, dear Mr. Paolo Della Ca, dear Mr. Daigo Rosseno, dear distinguished audience. On behalf of the Embassy of Italy in Tokyo, it is a great honor to address you at the close of this symposium on electrochemistry for a sustainable future. And I really regret not being with you in person. Today's discussions have highlighted how electrochemistry underpins the technologies we need to reduce our reliance on fossil fuels, from advanced energy storage to green hydrogen production, from resource recovery to sustainable industrial processes. Electrochemistry provides the foundation for cleaner, more resilient energy systems. The contributions we heard from Italian and Japanese experts demonstrate the strategic importance of this field for achieving carbon neutrality. This sector also offers remarkable opportunities for cooperation between our two countries. Italy and Japan share ambitious strategies for energy transition, and our strategic partnership, signed in 2023, places particular priority on green energy. So I wish to thank the organizer, Nora, whose presence both in Italy and Japan exemplifies the strength of our scientific and industrial collaboration. The Embassy of Italy is committed to supporting such initiatives. Last year, we promoted in Italy Innovation Day on Clean Hydrogen. In April 2025, we hosted all 5 Italian national PNRR centers for meetings with Japanese counterparts, particularly on sustainable mobility. At the Italian Pavilion, the Embassy co-organized the first Italian and Japanese Rectors Forum, which included the signature of 8 agreements between universities. And just days ago, here at Osaka Expo, an event on hydrogen and nuclear fusion, allowing the establishment of direct exchanges between ENEA and NEDO, and culminating with the signing of a memorandum of understanding between our national hydrogen associations. This milestone will foster even closer collaborations between our industries, research centers, and energy operators. Let me conclude by expressing my warmest wishes for the future success of your research and for the continued deepening of Japan-Italy cooperation in this vital field.
So then we're going to have one more closing remark from Daijiro Seno, Nora Perumelec.
どうも性能でございます。今日はこのエキスポ会場に入るのもすごく人がいて大変なところ皆さんご参加いただきましてありがとうございました。それでイタリアのこのパビリオン今回のエキスポの中でも非常に人気が高くて、なかなか長時間6時間ぐらい待たなきゃ入れないなんていうニュースも見ましたけれども。ここの館長のバッターニさんですね、本当にこの大阪エクスポで、成功、イタリアのことを大いに宣伝して成功させたいという気持ちで、いろんな仕掛けを作られて、みんなの興味を引くことを考えてくれただと思います。ちなみに今日、very sorry that our generous colleagues speaking in Japanese, but later I will interpret it. 今日エキシビションで皆さん伊藤満書の肖像画を見られたんだと思いますけれども、伊藤満書を天正のミッショナリーですね、ローマに行った1582年に日本を立って8年間ずっと世界インドからアフリカの方を回ってポルトガルから入ってスペインイタリアぐるっと回っていってローマ法王に謁見された。これが日本とイタリアのあるつながりの始めです。ロシアに大黒屋三太夫が漂流していったのが確か1680何年ぐらいかな。ですからそれよりも早い西洋との交流との長崎の方の少年使節団が成し遂げて、残念ながらその後キリスト教のいろいろな問題で鎖国という形になってしまって、途切れてはおったんですが、そうは言いながらもずっといろいろなその交流の中でイタリアとは日本は1866年に通商条約を結んでですね、来年が160周年になります。またイタリアの首相の メローニさんはご承知のようにすごくアクティブな、また保守的なことでも有名ですけれども、我々の日本の新しい総理大臣の女性もですね、またそういった形で竹内さんがなられるということで、日本とイタリア、また女性のパワーもさらに新しい力を生むんじゃないかと思われます。イタリアと日本は非常に似たようなところもいっぱいあるし、ますますいろんな形での協力関係というのが今後さらに発展していくんじゃないかと思います。これを機会にまたぜひデノラのことをしっかり頭の中に置いて、また我々とお付き合いいただけるとありがたいなと思います。今日は本当にお疲れ様でした。ありがとうございました。
はい、ありがとうございました。すみません、これでシンポジウムは終わりなんですけど、この後集合写真を撮りたいと思います。ご協力いただけるとありがたいです。So we're going to have a picture of all of us. So please, the speakers, please bring your seat here and make a line. So we're going to have a picture from that way, but just bring your seat here. Yeah, right, like that. Okay. で、この後ですね、please sit down. So please sit on your seat. ここの下の段に一列、それから各階段の上にそれぞれですね、列を作って並んでいただければと思います。すいません、ご協力をお願いいたします。